So the question is, if you've got a function that is, for example, maybe, well, let's do one that we can do some other way as well. X squared times the square root of x. That is the product of two functions. It's x squared times the square root of x. And therefore, it does turn out to be something that you can use the product rule to differentiate. However, this one can be done without the product rule, right? Because you can write square root of x as x to the 1/2 power. And then you can add those exponents. That would be x to the 2.5 power, which is the same as x to the 5/2 power. And that will mean the derivative by the power rule is 5/2 x to the 3/2 power, right? 5/2 minus 1 is 3/2. 2.5 minus 1 is 1.5. Yes, you could write these as decimals if you like, but I really think you should get practice with fractions. And again, if you're in this class and you feel like you don't like fractions, you always had trouble, you're not alone, but it is worth trying to improve on. That also could be written as 5/2 times x to the 1/2. In other words, 5/2 x times the square root of x. Let's check it with Mathematica. We want to get some practice using Mathematica today. One way to check this with Mathematica is to enter the function like I've shown you how to enter functions before. Remember, with square brackets and underscores after the variable name. And I could type x squared times the square root of x. I can use the palette over here. There's a square root symbol right here. I could hit that button and I see a square root. Do my shift return to enter that into memory. If you want to make sure it's in memory, you can type f of x like that. And there we see it's x. It's Mathematica simplified it to x to the 5/2. And we can compute f prime of x and see, yes, it is 5/2 times x to the 3/2, just like I have right there. I did just what you see. I typed f prime of x and entered it. Okay, Mathematica is computing the derivative there. Do notice, as a reminder, once you've defined the functions, don't use underscores anymore, okay? You only use the underscore after the variable right here. When you're defining functions, that's going to be relevant for the project as well. Is there a function I'd call g of x? Nope, I haven't defined g of x to be anything. Could I clear f? Yep, you can clear Mathematica's memory. Now f is not defined. If I hit the f of x here, it's not in the memory. If I enter f prime, it's not in memory anymore. But then I can re-enter that line and then it will be in memory. Okay, you can clear things from memory and then you can re-enter them and get them back in memory. But yeah, nothing is defined for g of x. Is there another way to differentiate this? I hinted at that at the beginning. Think of it as this product using this thing that I just called the product rule. Yes, there is. And what does the product rule say? I'm just going to write it down without explaining why it works for the moment. We will try to look at why it works, but not for the moment. What does the product rule say? It says if you want to take the derivative with respect to x of the product of two functions of x, I'm going to use an f of x times g of x, but realize if I apply this rule to this function that's labeled f of x, then I want to think of that function where I'm pointing here, x squared, as my f of x in the product rule I'm writing down, and this function, x to the 1/2, as my g of x in this product rule that I'm about to write down. Sometimes you think of f of x as being the first function. And the g of x as being the second function. Alternatively, or think of the f of x as the left function and g of x as the right function, meaning on the left and on the right. I always learned it when I was younger. And for teaching for like, I've been teaching at Bethel here for 25 years. For like my first 23 years at Bethel, I taught the product rule in terms of first function and second function. I said, hey, it's the first function times the derivative of the second function plus the derivative of the first function times the second function. That's kind of a mouthful. That is what the product rule says. But then I watched a 3 blue 1 brown video a couple years ago, thinking of it in terms of left and right, and it rolls off the tongue much faster. How does this roll off the tongue with the words left and right? It rolls off like this. Lefty right plus righty left. Done. Wait, what? What did I say? Left D right plus right G D left. I pointed at the wrong thing. I probably should have put those in the other order. Lefty right plus right D left. What's this D that I just said? D means derivative, right? Just a quick way of emphasizing derivative. Left function, D right means the derivative of the right function, plus right function, the G, D left means derivative of the left function. Left D right plus right D left. That rolls off the tongue faster than first times first. I suppose I could say first D second plus second D first. I always said the first function times the derivative of the second function plus the second function times the derivative of the first function. Yeah, that's a mouthful. It doesn't matter which way you remember it. Don't just start, but don't talk during the test. Think of it in your mind. It doesn't matter which way you remember it. Just realize this is the right formula to use. But again, its reason is mysterious. Why does this work? Let's see that it gives us the same answer in this situation up here. It better give us the same answer. So again, I'm back to the function up here. Let me go ahead and use the ddx notation down here. ddx of x squared times x to the 1/2 power. So my left function is x squared. My right function is x to the 1/2. Left d right means derivative of x to the 1/2, which I need the power rule for, is 1/2 x to the negative 1/2 plus right d left. I really should have written these two again in the opposite order to match that phrasing. Hey, this doesn't look the same as this, does it? Doesn't look like the same answer. Well, it's because you haven't simplified it. That's why it doesn't look like the same answer. Simplify. Add the exponents. 2 plus negative 1/2 is positive 3/2, right? 2 plus negative 1/2 is the same as 2 minus 1/2 is 1.5, 1.5, which is 3/2. And here we add the exponents again, we get 2 times x to the 3/2 again. 1 plus 1/2 is 3/2. These are like terms. You can combine them by just adding the coefficients, 2 plus 1/2, 5/2. Have you ever wondered why you can do that? Why can you combine those? Well, the official mathematical reason is the distributive property, because I can factor out the common factor of x to the 3/2 power. And then, yes, 2 plus 1/2 is 5/2. That's the official mathematical reason. A less official reason is, you got half of something plus 2 times the same thing. Like half of an apple plus 2 apples is 2.5 apples. And then you say, well, wait a minute, x to the 3/2 power is not an apple. Okay, just pretend it's an apple. I'm serious. Okay. As long as it's the same thing here and here, x to the 3/2, it's the same apple. It's not like an apple and an orange. We are really comparing apples with apples and not apples with oranges there. Okay. It's just a symbol. Yeah, it does represent a number. It represents the same number in both spots. So yes, the more official way is to use the distributive property to confirm that you can do that. Okay, so yes, we did get the same answer, 5 halves x to the 3 halves that we got up there with the power rule. So yes, the product rule worked. But why is the product rule true? You know, and if you didn't know the product rule, what might you guess would be true? You might guess that to differentiate a product, maybe it's similar to what happens with limits, right? The limit of a product is the product of the limits. You remember that property? Limit of f of x times g of x is the limit of f of x times the limit of g of x. So maybe the derivative of a product should be the product of the derivatives. Maybe it should be f prime of x times g prime of x. But that, if you try that here, it doesn't work. If you try just taking the derivative of x squared, 2x, and multiplying it times the derivative of x to the 1/2 x to the negative 1/2, you don't get the same answer. This simplifies to x to the 1/2, which is wrong, right? It doesn't equal that. We know that one works because of the power rule. So just trying some simple examples reveals that what you might guess would be true, that this should be f prime of x times g prime of x, must be wrong. And if you ever thought that, I'm not saying anybody ever did think of it, but if you ever thought that before, you're not in bad company. I think I remember Newton, maybe, and or Leibniz thought that was true first as well. But then they quickly realized they were wrong, maybe because they tried examples. So then it was a matter of coming up with the right formula. And I have no idea what kind of problem-solving process they went through to try to come up with the right rule. Was it heuristic? Was it example-based? I don't know. What I'm going to show you is the book's way of describing a way to derive the product rule formula. It's not an obvious thing that I'm about to show you, but it is kind of neat, I think. What you want to do is imagine it geometrically. Imagine a rectangle. And this is not just any old rectangle. This is going to be a growing rectangle. How do I draw a growing rectangle? Yeah, okay, you got to use your imagination. Imagine this rectangle is getting bigger. At some particular moment in time, call the time x instead of t, just to be consistent with using x as the variable. Maybe the length of this side is f of x, and the length of this side is g of x. So pretend x is time. I could use a t if I wanted to. And at a certain moment in time, x, f of x is maybe it's a function that's going to give you the length of that side, and g of x is some unspecified function that gives you the length of this side. I could have brought a ruler to class and I could have measured these to give you exact numbers in inches or centimeters or whatever, but I didn't. This rectangle is growing. After some small amount of time, call it delta x, it's become a little bit bigger. What's the new side lengths? How about f of x? Well, should I use a delta x? Okay, I could use a delta x. Let's use an h to be more consistent with the letter we use with the limit definition of the derivative, because that's what I got to ultimately use, is the limit definition of the derivative. So f of x plus h is a tiny amount of time that has elapsed. The rectangle has grown bigger. This side length now has that length, and this one has length g of x plus h. F and g are just functions that I'm not saying what they are, that I'm imagining to represent the side lengths as functions of x and pretending x is time. How is this relevant for the product rule? The area of the smaller rectangle, well, area of a rectangle is base times height, is f of x times g of x. Right? Base times height. The area of the bigger rectangle the entire thing here, is also base times height. F of x plus h times g of x plus h. That's the area of the entire big rectangle. Why do I do this? Let's start thinking about the limit definition of the derivative. I'm trying to derive the derivative with respect to x of the product f of x times g of x. By the limit definition of the derivative, that's the limit as h goes to 0 of a difference quotient. For what function? This product. F of x plus h times g of x plus h minus f of x times g of x. All divided by h. How is that related to this picture? Well, look at the numerator. The numerator is the difference in the function value, the function being f times g. Geometrically, that's this area of this sideways reflected L shape. This is the area that's shaded. Maybe that's useful. Maybe. It's not obvious that it's useful. How might it be useful? What am I trying to do here? How can I compute this limit if I don't know what f and g are? Well, remember what I just wrote down with the product rule 10 minutes ago. Lefty right plus righty left. That rule involved derivatives of f and g individually, and f and g themselves individually. If I'm going to compute this limit, relating it to f and g individually and f prime and g prime individually, maybe I'm going to have to somehow rewrite the numerator in a way that's easier to handle. And that's what this picture helps you do. Because that difference represents the area, if I figure out maybe an alternative formula for this area, maybe that'll be helpful. That's a common problem-solving strategy in lots of areas in math, is to think about something in a different way. That's what I'm doing. I'm about to think of this difference, which is this red shaded area, in a new way as the sum of these three areas. Now, that sounds worse because there are three areas, but they are all areas of rectangles instead of an L shape. So maybe that's better. They're all rectangles. What's the length of that side? It would be f of x plus h minus f of x, right? That would be the length of this side of this rectangle, right? Look at the picture. This distance from here to here is f of x plus h. This one from here to here is f of x. That distance right there should be the difference. It's also the side length of that little rectangle. I did make that look like a square, but it's not necessarily a square. How about the height of this rectangle? I guess it's related to g. Oh, it's just g of x. Right? G of x is the length right there. It's the same as the length right there. And coming over here, I guess this is the difference. G of x plus h minus g of x. Yeah, I'm feeling good about this because I'm seeing g and f numerators for their derivative limit definitions here and here. I phrased that kind of weirdly. In the limit definition of the derivative for f prime of x and g prime of x, these two things that I'm pointing at would be in the respective numerators. Oh, this is feeling good. It's not clear that it's for sure going to work out, but I'm feeling good about things. That distance right there is same as this one. It's f of x. And yeah, we've already figured out the sides of this little rectangle. So according to what we've just shown up there, it looks like this difference should be, at least based on the picture, the sum of the areas of these three rectangles. The first one having area equal to this times this. f of x plus h minus f of x all times g of x. That is the area of this rectangle here. Now add this rectangle here. It's going to be a very similar kind of expression, except switch the roles of the f and the g. Plus, in parentheses, g of x plus h minus g of x times f of x. All I did was just switch the roles of the f and the g compared to this one. And then the final, don't forget about the final tiny area. That is the product of this with that. That's the most complicated expression, actually, and it's the tiniest area, and I'm almost out of room on my paper. F of x plus h minus f of x, almost out of room, times g of x plus h minus g of x. Sorry that I ran out of room on my paper. That should all be on one line. All divided by h. Never seen a fraction like that before. Oh, we made it worse, didn't we? No, it's better. It just looks worse. Is it really right? Can you really trust the picture? That's what I'm doing, right? Is I'm really just trusting this picture. Can I really confirm that all this mess really equals that if I didn't look at the picture? Sure, you could double check it by simplifying the top. You could just use the distributive property. You'd have to FOIL here. And evidently, everything cancels except for these two things. And yes, it does happen. You can try it. Bit of a pain. It would take us 5 to 10 minutes. I don't want to do it. Okay. It works. But now, how do we finish it here? Well, I've got really, a big fraction with a big numerator essentially split into the sum of three things all over the same denominator. I could split those into three separate fractions that are being added because they all would have the same denominator of h. And then the limit of a sum is the sum of the limits. I can have the limit of the first fraction careful not to make a typo, plus the limit of the second fraction. Fun, fun, fun. Okay, yeah, I'm getting tired of writing, but it's worth doing once in your life. I hope you are taking notes. Well, maybe not. It's in the book. Actually, the book makes it a little bit more convenient using a shorthand notation, calling this delta F and this delta G just makes it a little easier to write. And this would be delta F times delta G. All right, well, I'll write it out, though I am running out of paper again. You've never seen fractions with curvy lines like that before. All right. Are we done? Stop the agony. Remember, when you're computing limits like this, you think of x as fixed. H is the variable for the limit. So any factor that just involves an x, like those two, can be factored out in front of the limit sign. So we get, that's like a constant with respect to the limit. We get g of x times the limit as h goes to 0 of f of x plus h. Oh, this is feeling so good. Minus f of x divided by h. And that limit is f prime of x, the derivative. If the limit exists. Oh, wait, do I have to really think about limit might not exist? No, you don't, because you just assume it exists. And is that cheating? No, it's not, because whenever you have theorems in math, like the product rule, you make assumptions. And in this case, we'd assume f prime and g prime of x both exist, that f and g are differentiable at whatever value of x you're talking about. That's okay. That's the way the game of math is played. Oh yeah, and there's going to be the limit for g prime. That's g prime of x. So look at, we have, well, right d left plus left d right. But wait a minute, what about this thing? To save time, I'm just going to put question mark, question mark, question mark. That looks like we have this extra thing that's going to make the product rule not work. And here we just have to be a little bit hand wavy to say question marks are 0. Wait, really? What? Huh? Okay, we're not proving it's 0, but let's give an intuitive argument for why it's 0. You want to imagine this picture for h really, really small. If h is really, really small, this red area, this L shape, is going to be really skinny. If h is small enough, that skinny L shape is going to have a small total area. More importantly, the upper right corner of it is going to have a really, really tiny area. In the limit as h goes to 0, the product of those two areas goes to 0 faster than h does, effectively. It's kind of similar to the fact that when you square a really small number, it becomes even smaller. You know, 0.1 squared is 0.01. 0.01 squared is 0.00001, 10 to the negative 4. 0.000001, which is 10 to the negative 6, 1 millionth. When you square it, it becomes 1 billionth, 10 to the negative 12. 10 to the negative 6 is 1,000,000 times bigger than 10 to the negative 12. Now, if you've had a lot of science courses, you feel comfortable with that. If you haven't had many, it's kind of hard to imagine that 10 to the negative 6, this small number, could be a 1,000,000 times bigger than 10 to the negative 12. But it is. If you scaled up your number line in such a way that you could see this one, that would be too small to see. So effectively, this product goes to 0 much faster than h does. It's like an h squared, say, compared to h, making the fraction go to 0 as h goes to 0. That's not a proof. It's an intuitive reason why this limit is 0, and therefore we do get the final answer. In this case, written right d left plus left d right, but you know, addition is commutative, so that's the same as left d right plus right d left. Okay, it's still the product rule. Let's apply the product rule to another example. Let's let f of x be, oh, how about x squared e to the negative x. I'd like to find the derivative of this. It is the product of two functions, x squared and e to the negative x. And I'm calling it f of x. So do I want to call that f of x and that g of x as well? Not really. And in fact, you aren't typically wanting to actually write down the product rule when you use it. You're just wanting to think it. The derivative of this is left d right. What's the derivative of e to the negative x? By the rules we have so far, we need to use the fact that this equals that. We can't use the chain rule yet. You may not know what the chain rule is yet. The derivative of this, we need to use the fact that the base here is e to the negative 1, is going to be natural log of e to the negative 1 times that base to the x power. Natural log of e to the negative 1 is negative 1. This simplifies. This is e to the negative x. So that's left d right. This is left This is d right plus right, e to the negative x, d left, 2x. That's right, d left. When you show your work, you don't have to write the left d right plus right d left stuff, okay? That might confuse the grader, actually. Simplify becomes negative x squared e to the negative x plus 2x e to the negative x. There's the derivative. By the way, on the gateway, don't do it this way. Use the chain rule, which I will try to introduce you to very briefly at the end of class today, though you won't have any homework on it. Don't do it this way on the gateway, okay? I mean, I know what you're doing, but if I had a grader grade it, okay. You don't want to do it this way. But anyway, that is the right answer. That's good enough for the gateway. It's good enough for a homework problem where you're just taking the derivative. But for the purposes of using the derivative, we can use derivatives? Using the derivative to do what? Oh, to like help you graph this function without a calculator, for one thing. It's good to try to factor if possible. Are there any common factors in both terms? Sure, there's an e to the negative x in both terms, and there's also an x in both terms. That can be factored out. What's left over? A negative x plus 2 is what's left over inside the parentheses, right? Double check that. Imagine using the distributive property to go backwards. This is a good idea for the purpose of using the derivative because it helps you figure out where the derivative is 0 and positive and negative. And why would that be important? Because it helps you figure out where the original function has a graph that has a horizontal tangent or a positive tangents or negative tangents. And where it has positive tangents over some interval, it's increasing. And where it has negative slope tangents over some interval, it's decreasing. That helps you graph the original function. In this case, f prime of x equals 0 if x is 0 and, well, or x is 2. It's actually 0 at both of those spots. Let me not put the word if in there. Let's say at x equals 0 and x equals 2. And let's see, when x is between 0 and 2, like 1, is it positive or negative? If you plug in x equals 1 into this, you get a positive number. F prime is positive between 0 and 2. And if you plug in a number bigger than 2, like 3 times e to the negative 3 times negative 1 is negative. F prime is negative over here. This is the number line. And if you plug in a number like negative 1, you also get a negative derivative. F prime is negative over here. That tells you the original function, x squared e to the negative x, is decreasing in here, increasing in here, and decreasing right there. And I can tell you, based on experience, that the graph of f looks about like this. This is the graph of f of x equals x squared e to the negative x. And it has a what's called a local maximum at 2, where the derivative is 0 and the derivative changes sign from positive to negative, and on what's called a local minimum at 0. Without a calculator, I can quickly graph x squared e to the negative x by thinking about how the derivative changes sign. You can also plug numbers in, like you can see f of 0 is 0. That's necessary to know as well to fully make this graph. What is f of 2? Well, it's 4 e to the negative 2, whatever that is. 4 e to the negative 2 if you plug in x equals 2. Whatever number that is. It's less than 1, actually, but some number.